Okay, welcome back, everybody. Um, so, yesterday we gave definition for these binomial coefficients. Of course, it was clear where they arose, right? Even the way you read off this symbol many times in choose k explains where the need for such an expression comes from. Um, we noticed that choosing k is the same as choosing n minus k. So there's this symmetry. Um, you might not immediately see why this is symmetry. When we do something here in a second, you're going to see it more. Um, we had this addition formula, which is you could think of as you're summing in the lower index here, right? This is k plus k minus 1 gives you this. The result being this n choose k is obtained from this sum. I promised that we would prove this today. So there's a number of ways to see this, but maybe the most direct way is to just write out this thing in terms of just expanding both of these in their usual factorial form and then doing a little bit of algebra here. So let's do that. So let's see. Proof is next time is now. So now we're doing it. What if I'm going to start with the right-hand side. So the right-hand side here is n minus 1 choose k plus n minus 1 choose k minus 1. I can assume that k is strictly between 0 and n because if it's not, then it's easy to see that this formula holds, right? If it's not, then I mean this is what we're left with, this or 1, right? So it's easy to see in either case. Um, and so this, if I just write this out in terms of what it is, this would be n minus 1 factorial over k factorial times n minus 1 minus k factorial. Okay, plus n minus 1 factorial over k minus 1 factorial times n minus k factorial. This would be n minus 1 minus k minus 1 minus 1 plus 1, so this would be n minus k factorial. Okay. So now I want to get a common denominator. The common denominator I am going to seek here is k factorial times n minus k factorial. Now, you may be able to see, just looking at this algebraically, that that is going to be a not so hard common denominator to get. You might also think in a way of, well, if I've already noticed this pattern before, right? So we noticed this pattern in our previous poker hands example. So this was the basically noticing that a hand either has the ace of spades or doesn't, and we counted the number of ways it could have ace of spades versus not, and this is where we got this pattern from in the first place. So maybe you know already what you're seeking. So you know that the denominator of this is k factorial times n minus k factorial, and that's what you're trying to mimic. So let's in either case, let's do that. So I'm going to get a common denominator of k factorial times n minus k factorial. But to do that, what do I need? So here I already have the n minus k factorial. I need a k factorial in the denominator here. I have k minus 1 factorial. Well, k minus 1 factorial times k is k factorial. And so I could multiply by a k in the numerator and denominator, which will give me a k factorial n minus k factorial here. Okay, good. Here I already have a k factorial, but I have n minus 1 minus k factorial. So what do I need to multiply by here to get an n minus k factorial? Right? What do I need to multiply by? Well, I can multiply by n minus k, right? So if I multiply by n minus k, that's going to do it, which means in order to keep everything the same here, I need to multiply by n minus k in the numerator as well. So what does this lead to? This leads to n minus k. I'm factoring now, if you like. I'm going to factor out an n minus 1 factorial here. So what I get is n minus k plus k times n minus 1 factorial. But minus k plus k, those cancel, and I'm left with n times n minus 1 factorial. So I'm left with n factorial over k factorial times n minus k factorial, but that is exactly n choose k. So that's it. Okay, so just a little bit of algebra there using the definition of this thing gets me what I want. Okay, but thinking about how this works, the thing that might be more instructive is rather than thinking about this and how you could derive this, is thinking about this previous example that we did yesterday that illustrated this pattern. Okay, now using this together with our other facts here, we can generate a table of values for these things. And so, why don't I pull up such a table? There we go. But, of course, we know what this is. Viewed in this way, it might not look like the familiar thing that you're used to, right? Changing the way this is plotted ever so slightly to make maybe a more pleasant aesthetic arrangement here. This is, of course, just Pascal's triangle. And of course, this here, k goes across the top, n goes down the side here. The way to think about this, of course, or one way, rather, to have derived this otherwise, is you could tell a student even that had no idea what was going on combinatorially how to generate Pascal's triangle. Of course, you recognize what's going on here. And now it becomes clear what the symmetry is, and so on. Okay. So, how to read this? So at each level, I am at the, so this is the n equals 0 level. This is the n equals 1 level. This is the n equals 2 level, n equals 3, n equals 4, and n equals 5. And then the k level, like if you view it in this way, the k equals 0 are these terms, k equals 1 are these terms, k equals 2 are these terms. You'll notice that when k is equal to 1, of course, this is n choose k, or n choose 1, it's always going to be n. So when n is equal to 1, it's 1. When n is equal to 2, it's 2, 3, 4, 5, and that's going to count up in that fashion. Okay. Of course, you noticed, again, what I was saying before about you could have, a kid generate Pascal's triangle, and likely that's the first place you saw it as well, is, even just noticing the pattern that to get any of these particular coefficients, you sum the two coefficients here and here, right? That's why I arrange it in this way, to make the pattern a little bit more obvious as to what's going on here, right? So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and so on, right? This is how this thing is generated. Of course, this is also touching on one of the original places these things actually showed up. They show up combinatorially naturally from this problem, and it's the reason they're called the binomial coefficients. It is because of the binomial theorem. So what does the binomial theorem state? If n is an integer, it's non-negative, then if I have the binomial term x plus y raised to the nth power, this can be computed as the sum over k of n choose k times x to the k, y to the n minus k. This is very important for a variety of reasons. We'll see that this gives us a way of computing the number of elements in power sets very, very easily. This binomial coefficient naturally arises as a counting thing, because when you try to expand a thing like this, right? You try to expand an x plus y to the n, right? So think of n equals 2, n equals 3, n equals 4. What you are in effect doing at each step is you're trying to group the like terms in this expansion. When you actually do this, if you were to expand this out and just by hand multiply, say, x plus y to the fourth, right? You would expand that out fully, then you would group the like terms, the terms that can be combined, where, you know, for instance, your x1, y cubed terms would all get combined. Your x squared, y squared terms get combined. Your x cubed, y terms get combined, and so on. When you're combining those, you're essentially asking the number of ways you can choose k objects from n at each step. So in the event of say n equals 4, you are asking how many ways you can choose the k powers making up each of the terms is going to have degree 4 in x and y. So you're basically asking how many ways you can distribute those powers at each step. Anyway, we're going to prove this with induction. There are other ways to prove the binomial theorem. Before the proof, here's an application. Of course, I can use this to instantly expand, say x plus y to the fourth. Instantly, I can use, this is x to the fourth plus 4x cubed y plus 6 x squared y squared plus 4 xy cubed plus y to the fourth. And that is just by reading off these coefficients, 1, 4, 6, 4, 1, and paying attention to how the powers of x are counting down, powers of y are counting up. The degree of each term is 4. That is, the sum of powers between x and y is always 4 for each of these things. Of course, you might say, well, maybe I'm not as interested in that. Maybe I'm more interested in say something like this, x plus 2 cubed. Well, again, here I'm using this, so this is x cubed plus 3 x squared times 2 to the first plus 3 x times 2 squared plus 2 cubed. So this would be x cubed plus 6x squared plus 12x plus 8. All right, another quick application of the binomial theorem. Of course, this is its bread and butter. This is what it's made for. We'll see. So we'll see more after we prove it. Of course, this doesn't have to be a plus. You could do this with you could do this with say x minus 1 to the fifth. You could rewrite this as x plus minus 1 to the fifth and use the binomial theorem. This just gives you an extremely convenient way of quickly expanding a binomial in this way. So whenever you have some, say, nasty algebra that needs to be done, you need something expanded, and you don't want to actually do the full distribution, multiplication, all that, you can use binomial theorem. It's easy to do it this way. There are a number of ways that this is used, for instance, to say when you are doing some kind of algebra involving whether or not you care, or if you're doing like modular arithmetic is another place this comes in, where maybe some of these coefficients in the middle, they are 0 mod some integer that you're working with, so a lot of them drop out. Maybe all of them drop out. So anyway, lots of uses for this, obviously. But I'm going to do a proof of it real quick. So proof of binomial theorem. So standard proof by induction. Just very quickly to remind you, the sum that I'm doing is technically, I wrote it as a sum over k on purpose, because the way that this works is you could think about this as a sum over all integers, but of course, because n choose k is only non-zero when k is strictly between 0 and n, all but finitely many of these terms are 0. So this is a finite sum here, even though I'm writing it as an infinite sum. This is actually a finite sum. Let's use induction. So we are going to use induction on n. If n is equal to 0, both sides are 1. Just bring it back on the screen here for a second. If n is equal to 0 here, then the only single term is a 0 choose 0 term here, which is 1. Here, this would be x plus y to the 0. That's going to be 1, so 1 is equal to 1. That's fine. So good, that's our base case. Doesn't get any easier than that. So suppose the result holds for a fixed non-negative integer n. We want to show it holds for n plus 1. Okay. So we use the inductive hypothesis, and we are going to do the following. This is always our standard induction trick when you're dealing with sums here. Let's say that I have x plus y to the n plus 1. Of course, this can be rewritten as x plus y times x plus y to the n. And I know that by our induction hypothesis, binomial theorem is true for this term. So of course, this is what I get in place of x plus y to the n. So this is x plus y times the sum over k of n choose k times x to the k, y to the n minus k. Okay, so what to do now? Well, I'm actually going to distribute this sum across, I'm going to distribute this sum here across this parentheses so that I'm going to have x times this sum plus y times this sum. In both cases, essentially what I'm doing is just adding a power of x in the first term and adding a power of y in the second term. So I'm going to distribute this to get two sums. The first is the sum over k of n choose k times x to the k plus 1 times y to the n minus k, plus the sum over k n choose k times x to the k times y to the n plus 1 minus k. Okay. Now, what I'm going to do is reindex the first sum. So reindex first sum. Again, depending on how much probability you have had, this is a trick that is used extremely commonly when these things come into play. The reindexing of sums here to get what you want to make the algebra work out. So here, how am I going to reindex this? I want to replace each occurrence of k with k minus 1. This again shows us why it's nice to have this as just a sum over all k, because if we're summing over all k, then this reindexing is something we can easily do. It's just going to be over all values of k as well. So I don't have to worry about whether I'm starting at 0 or 1 or something like that, right? Although, of course, that is still hiding in the background, and it's not going to matter in this case. But this is just another reason why I don't even have to. I can just leave this as a sum over k. So how does this go? So replace k with k minus 1. If I do that, then this, of course, is going to become sum over k of n choose k minus 1, right? Why can I leave this sum over all k? Well, because again, this reindexing is not going to change the fact that this all values of k are being summed over here. So this is n choose k minus 1 times x to the k, because k has been replaced with k minus 1 here. So k minus 1 plus 1 is just k, times y to the n plus 1 minus k, plus, I'm just copying this second sum from before. Now, you might have said, why would we have done this reindexing in the first place? Why would you have gotten this idea? You would have gotten this idea basically trying to match up the terms here and coming from this previous fact, the addition fact. So you're using your intuition saying, I know this is the case, and I also want to match up these terms here so that these can be combined. So, rewriting this and regrouping, this is the sum over k of n choose k minus 1 plus n choose k times, these terms are the same for both of these sums, x to the k, y to the n plus 1 minus k. But by our addition formula, n minus 1, choose k, plus n minus 1, choose k minus 1. That is what I have here, except instead of n in both of these, or instead of n minus 1 in both of these, I have n. And so what I get here, after using the addition formula, I get sum over k of n plus 1, choose k, times x to the k, y to the n plus 1 minus k. Which is exactly the binomial theorem, except with n replaced by n plus 1 everywhere. So I have shown that this result holds for n plus 1. So I'm done with the induction. And the binomial theorem is true. Okay. Now, two facts to notice. I should maybe just directly call them consequences. I showed you a couple of applications, of course, like the obvious applications of the binomial theorem, the thing it was literally made to do. So that might, you might not view that as particularly impressive. But notice, set, here, I'll call this the first consequence. Set x and y both equal to 1 in the binomial theorem. Well, if x and y are both 1, then this is 1 plus 1 to the n, or 2 to the n is equal to, we're raising 1 to any power is just 1, so this is 2 to the n is equal to the sum of these binomial coefficients. So 2 to the n is equal to the sum of these binomial coefficients. So this is the sum from k equals 0 to n of n choose k. That's neat. What does this mean? Of course, it means if I sum across the nth row in Pascal's triangle, then I get this power of 2. So for instance, if I sum across the rows here, 1 plus 1 is 2, which is 2 to the first. 1 is 2 to the 0. Here, 1 plus 2 plus 1 is 4, which is 2 squared. 1 plus 3 plus 3 plus 1 is 8, which is 2 cubed. All right. 1 plus 4 plus 6 plus 4 plus 1. This is 16, which is 2 to the fourth. 1 plus 5 plus 10 plus 10 plus 5 plus 1 is 32, which is 2 to the fifth, and so on. Okay, so summing across each row in Pascal's triangle gives you 2 to that power. But while that's true, the important thing going on here is that actually this is giving you an interesting count. Think about what the right-hand side is counting. The right-hand side is counting the sum of subsets of size k from a set of size n, and it's all of them, right? So what do I mean by that? What is this right-hand side counting? All subsets of a set of size n. How do you figure? Well, what is n choose 0? Say, I've included that just for this reason, to say this. This is the number of size 0 subsets of a set within elements. But, I mean, this is true for any of these, right? This is the number of size 1 subsets. And of course, n choose k is the number of size k subsets of a set of size n. When we say size, we mean cardinality here. We're talking about sets. So, I am adding on the right-hand side the different size subsets of a set of size n, right? So it's all of the size 0 subsets, size 1, size 2, size 3, all the way up to n. Of course, there's exactly one way to choose n elements from a set of size n, right? So what this says is that the number of subsets of a set with n elements is 2 to the n. This is probably the easiest way to compute this fact. Okay, this gives us the cardinality of these finite power sets, is what they're called. That is, you start with a set and then you consider the set of all subsets of that set. That's the power set of that set. So the set of all subsets of a set size n has cardinality 2 to the n. Okay, so we get that directly from the binomial theorem. Another fact. What if I set x equals to -1 and y equals 1 in the binomial theorem? Well, of course, -1 plus 1, that's 0 to the n. Here I'm going to get 1 to the k, or sorry, -1 to the k and 1 to the n minus k. So what I'm going to get is an alternating sum here, right? And that is going to be 0 in all cases unless n is equal to 0. So what I get is that the sum over k of -1 to the k times n choose k is 0 if n is greater than or equal to 2, and 1 if n is equal to 0. We have to include that case just to make this nice, but what does this say? Alternating sums of rows in Pascal's triangle are 0 if n is greater than or equal to 2. All right, of course you could verify that yourself. Right, so 1 minus 2 plus 1 is 0. 1 minus 3 plus 3 minus 1, 0. 1 minus 4 plus 6 minus 4 plus 1, 0. And so on. Okay. So, of course, you might have said, well, I know that there's symmetry, so I knew this was going to work. But that's easy to say when n is odd that it's going to work from symmetry, but when n is even, it's maybe a little bit less obvious that this would be the case. But with the binomial theorem, yeah, we got this immediately. Okay, more binomial coefficient facts. The next property is referred to shorthand as summing on the upper index. So summing on the upper index. If m and n are non-negative integers, let's see here, m and n are non-negative integers, then the sum from k equals 0 to n of k choose m is equal to n plus 1 choose m plus 1. Okay. This is here, this sum is summing on the upper index in this binomial coefficient. The result of summing in this way is actually just can be encoded in a single binomial coefficient, n plus 1. Choose m plus 1. Okay. So again, maybe you hate this. We're going to use induction again, right? The old joke that induction is what you do when you don't know what to do. So we use induction. But if you're thinking about it more like an experimentalist here, right, then maybe you like this even better, because the idea is that you would generate a few examples, you would notice a pattern, you have your suspicions that the pattern holds. Maybe for all the examples you can do by hand, or you do it out to satisfaction using a computer, and you notice that the pattern holds for all those, and then you say, oh, well, I can, realistically, if you're coming up with this relationship, of course, you'd be doing this before computers existed. But you do this for, a few examples. You notice the pattern, and then you think you know what the pattern is. So having to know the answer is not that big of a deal when you're generating a bunch of examples that fit, this supposed pattern you're trying to recognize. So it's okay, it's fine. Just because we have to know what the answer is before we start here, it's fine. So okay, I'm going to use induction here for n equals 0. This is true. Again, both sides are equal to 1 in that case. Well, both sides are equal to 1 if, I should say, if m is equal to 0, both sides are 1. And if m is greater than 0, both sides are 0. Again, this is giving you some more motivation for why we defined these things the way we did. But anyway, in either case, this is true. So now it's time for the induction step. So we suppose the identity holds for n. We want to show it holds for n plus 1. So suppose identity holds for some fixed, generic, arbitrary n greater than or equals 0. Want to show it holds for n plus 1. Okay, so now to do this, let m be some generic non-negative integer. Let's just see what we can do here. Of course, our strong desire is to split this up and apply the inductive hypothesis to the sum up to n, since we're assuming that's true, or that has this form. So I have split off the top term here, which is n plus 1 choose m. I split that off from the rest of the sum, which is the sum from k equals 0 to n of k choose m. Of course, by the inductive hypothesis, this is n plus 1 choose m plus 1, so this is n plus 1 choose m plus n plus 1 choose m plus 1. But hey, by the addition property, let's remind ourselves, by the addition property, well, what is this? This is n plus 2 choose m plus 1. Which is exactly this expression, except I've replaced n with n plus 1 in both cases. So the induction is done. Okay. All right. So before we mention something else, I have one more identity. Maybe I think. The question is, do I want to do the full motivation for this identity, or do I just want to give you the identity and have you read over it? Let's go ahead and just do the full identity here. I think that is fine. So notice in the following example. So this example uses what is called Lotto Texas game. So what is the idea here? A player selects 6 different numbers between 1 and 54 to enter in the lottery. Okay, player selects 6 numbers between 1 and 54. This is the lotto ticket. The largest prize is awarded to anyone matching all 6 numbers picked in a random drawing by lottery officials. Okay, so top prize matching all 6 numbers. Okay, but smaller prizes are given to players matching at least 3 of these numbers. So smaller prizes given is matching at least 3 of these numbers. What I say by matching, what are we matching them to? I mean, obviously you're picking 6 numbers between 1 and 54. A drawing takes place, a random drawing of, say, ping pong balls that have been numbered appropriately from 1 to 54. These are, this is randomly done or randomly generated in some way. The numbers drawn, there's 6 of them drawn, and the question is, how many do you match? If you match all, that's the top prize. If you match at least 3, you get some smaller number of prizes, and the amount of money you get is going to depend the number of possible tickets that match exactly K of the winning numbers for every K. So question, what is number of possible tickets matching K numbers for each K? Of course, you can match either 0, 1, 2, 3, 4, 5, or 6, so there's not a lot of options for how many can match, but we have to compute how many tickets exist for each of these things. So let's just do this one at a time, right? What number of ways to match all 6? You might just immediately notice, well, there's only one way that can happen. Whether you got that from 6 choose 6 or not, well, maybe you did, maybe you didn't. But what's the number of ways to match 5 of the 6? Not at least 5. This would just be exactly 5. Well, there would be 5 choose 6. Sorry, read this backwards. 6 choose 5 numbers or number of ways to pick 5 of the 6 matching numbers. But then I still need to pick a 6th number that's a losing number here. And if there are 6 numbers between 1 and 54 here that I am trying to not hit, right, because I don't want to match, then I have 48 numbers to select from, remaining. So this would be 6 choose 5 times 48. But 6 choose 5, that's 6. So this is 6 times 48. So that's 288 possible tickets here that match exactly 5 numbers. What about the number of ways to match exactly 4? How would I do this? Well, I need to pick 4 from the 6 winning numbers and 2 from the 48 losing numbers. Right? So this is 16,920 tickets. And in general now you should see how this is working. So number of ways to match exactly k is 6 choose k times 48 choose 6 minus k. And so the number of total ways to match at least 3 numbers would be obtained by summing over these sorts of terms, where k is 3 or greater, right? So I can count every possible ticket exactly once. So counting every possible ticket yields the following. Of course, the total number of tickets is 54 choose 6. But counting every possible ticket exactly once via this formula is just me summing over k here. So this is the sum over k of 6 choose k times 48 choose 6 minus k. Now why does this count everything once? Well, think about what each term in this sum is counting. It's the number of ways to match exactly k in each term. So the number of ways to match exactly 0, 1, 2, 3, 4, 5, 6. All of these are being counted. And the way that we have selected these means we're not like double counting this here. Of course, I can use this to generalize the following. So now, if a lottery requires selecting m numbers from a set of m plus n numbers, then using the same reasoning, we have the following identity, which is m plus n choose m is equal to the sum over k of m choose k times n choose m minus k. Okay. But then what does this say? This says that the number of possible tickets equals the sum over k of the number of ways to match exactly k of the m winning numbers and m minus k of the n losing numbers, right? So I'm summing over k. This is number of ways to select k winning numbers, and this is number of ways to select m minus k losing numbers. So there are n total losing numbers, right? Just like there are m total winning numbers. Okay. Now, further, if a lottery game requires a player to select L numbers on a ticket, and each drawing selects M winning numbers, if a lottery requires a player to select L numbers on a ticket, each drawing selects M winning numbers, then, using the exact same reasoning here, M plus N choose L is the sum over K of M choose K times N choose L minus K. So now, keep going. I can replace L by L plus P. I can reindex the sum, replacing K by K plus P to obtain the following identity. So replacing L by L plus P and K by K plus P and reindexing, I get the following identity, which is called Vandermon's convolution. So why this is called a convolution will remain mysterious unless you have taken a little bit of probability. You'll see that this, what I'm about to write here, is like the discrete version of what is continuous convolution. So if you have any familiarity with what convolution of functions are, this is something that's done in a variety of contexts, differential equations. Otherwise, this is involved in what's called the mollification or smoothing of a function. So what is Vandermon's convolution? This is the statement that if m and n are non-negative integers and L and P are integers, so m and n are non-negative integers, L and P are integers, then m plus n choose L plus P is the sum over K of m choose P plus K times n choose L minus K. So I did this whole explanation, this whole example, so that this would seem less mysterious when you see it. As I said, this is saying that the lower indices in the binomial coefficients on the right-hand side, these sum to a constant. You'll notice they sum to an L plus P here. in each term. Okay, so when you actually use this, you'll see that in the pattern. But anyway, I just wanted you to see where this came from, rather than it just be spat out of nowhere. But that's the last of the named identities we're going to talk about. There are many, 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 many other identities involving binomial coefficients, so this isn't an exhaustive list. Some of the exercises that you're going to do after Thursday will involve proving some of these. Um, so that's the deal. And so it seems natural then to move on to the next generalization of these sorts of objects, which are multinomial coefficients. Now we're going to see, spoiler alert here, the thing is that we're going to see that multinomial coefficients don't I'm not going to say they don't exist. They clearly exist, but it's kind of a bit like logarithms that are not the natural log, right? But once you have the change of base formula for logarithms, any logarithm can be put in terms of the natural log. Natural log is the best log. So whenever you see a fact, if you just really hate, right, log base 2, log base 10, log base 12, whatever, if you just absolutely hate using other logs, well, technically you could just always use the natural log using the change of base formula, right? So every log is a natural log in that sense, and there's a reason why the natural log is like biased in certain applications and why you'd want to use it versus some other log. So that's a nice fact. So in the same way, every multinomial coefficient is actually just binomial coefficients, but there are legitimately applications where there's no reason to use the middleman. We can just use the multinomial coefficients, right? Just like how you know, you're all CS people. You know that log base 2 and other base logs are useful without having to pass to the natural log, even if technically every single argument you've ever seen in your algorithms class involving log base 2 or whatever, could you have done the same thing with natural log? Absolutely, but right, why? There's no need to do it. So anyway, that's the point. That is the good news, that if you just really like binomial coefficients and you want to use those instead, you can, if you want to. But there are reasons why this is nice. So let's see how this is a direct generalization of binomial theorem with the following example. So suppose that I have n objects, so n distinct objects, and I want to place them in two boxes. We will call first one box A, the second one box B. Okay. And so n objects placed into two boxes, box A or box B. And let's say that in box A, I've placed lowercase a number of objects, and in box B, I've placed lowercase b number of objects, and that this exhausts all of my objects, which tells me that a plus b is equal to n. Okay, let's assume that the order of the placement doesn't matter. I'm not tracking in what order I place them, so I'm just tracking the end result, right? So at the end result of placing these n objects in the box, I'm just checking the number of objects that are in each box. That gets labeled little a, little b, and of course those have to match. None of the objects went anywhere else. Okay, and so the total number of such arrangements, so total number of such arrangements, or phrased in another way, the number of ways to place n objects into two boxes such that box A receives little a objects, box B receives little b objects, is exactly this number I'm computing. So the total number of such arrangements, let's define that by this symbol, which is going to be written almost like a binomial coefficient, but it's n and then a comma b here in the second slot. Now, we can actually compute this. Note, this thing can be computed because once I know that I have selected little a objects for box A, that fixes what little b has to be, right? So because there's only two boxes here, once I know, right, imagine I have 10 objects here, right? Once I know I've placed 3 objects in box A and that's it, I know that the other 7 objects have to go to box B. So fixing little a fixes little b, right? So actually I can compute this with a single binomial coefficient. So notice that this is just n choose A. But also, this is n choose B. In fact, in both cases, this is n factorial times a factorial times b factorial. So this is n factorial divided by, sorry, I think I said times there when I was writing it out, n factorial divided by a factorial times b factorial. Why does it work this way? Well, again, a plus b is equal to n, so b is n minus a. So n factorial over a factorial times n minus a factorial, of course that's n choose a. But the same can be said of b. A is equal to n minus b. So same thing is true here. Right? There's this symmetry. And so actually this is just a binomial coefficient normally. Now, to see that we can generalize this just a little bit, what if instead I have n objects placed into 3 boxes? So those boxes are A, B, and C. And I have put little a objects in box A, little b objects in box B, and little c, which I have written as n minus a minus b. So that now this is fixed. If I know how many I'm putting in box A and box B, then how many I'm putting in box C is fixed. Of course, A plus B plus C is equal to n here. And I could ask for the total number of such arrangements, which I would compute using this symbol. But what is this? I'm going to use the product rule here. So, even from before, this is n choose A, and then the remaining objects I have is n minus A, because I've placed A objects in the first box, and now I'm choosing B from what's left. Once I have done that, I have fixed how many objects are placed in box C, so there's nothing to do. This is the last step in this process, right? Once I've selected how many I'm putting in box A, that's the first step. Then from the remainder, if I put little a objects into box A, then there are n minus little a objects left. I place B of those into box B. Then I'm placing C of those, however many are left after this step. C of those get placed in box C automatically. There's nothing else to do, so there's no choice here. So nothing is contributing to this count anymore. So let's just see what this is. This is, by definition, this is n factorial over a factorial times n minus a factorial times n minus a factorial over b factorial times n minus a minus b factorial. Again, this is just the definition of these two binomial coefficients. N minus a factorials cancel. N minus a minus b, that's c. So this is n factorial over a factorial times b factorial times c factorial. This expression is called a trinomial coefficient. And now you see where we're going with this. So we can use this pattern that is emerging here. You could do the exact, if you really want to nail down your intuition for this, do the exact same thing with 4 boxes. You'll see how this is going to work. This allows us to talk about multinomial coefficients. So the multinomial coefficients are defined as follows. So definition. Okay, so let's say we have n objects, m boxes, labeled 1, 2, and so on out to m. Suppose k1, k2, up to km are non-negative integers. Such that they sum to n. Okay. The multinomial coefficient which is n and then k1, k2, and so on out to k sub m. This is defined to be the number of ways to place k sub 1 of the objects in box 1, k sub 2 in box 2, and so on without regard for order. Okay. And we mean that by we don't regard what the order is of placing any of the objects in any of the boxes. Okay. Now, here is a quick fact that we are going to prove simultaneously, that this multinomial coefficient, if I want to think about doing this process, well, I am taking n objects, I have n objects total, and k sub 1 of them go in box 1. Then from the remainder, which is n minus k sub 1, I am placing k sub 2 in box 2. And then from what is left from that, I am placing k sub 3 in box 3. And I continue that process on until I get to the last bit where the remainder is n minus all of the amounts of objects I've placed in all of the boxes up until now, k sub m minus 2, because we're on the second to last box. I place k sub m minus 1 in the second to last box. At this point, it is completely determined how many objects I have left, and all of those go into the very last box. So there's nothing else contributing to this count. If you do the algebra here, similar to how we did in our case, we will find that this is simply n factorial over k sub 1 factorial times k sub 2 factorial times k sub 3 factorial, and so on, all the way out to k sub m factorial. Okay. And so this is our expression for multinomial coefficients. Just like with binomial coefficients, it's useful to have this expansion where if any of the k's are not the right size, we zero these out. This allows us to have sums that go over, say, all integer values, so we don't have to worry about exactly how many terms are there. We just know that it's a finite sum. So I want to state a few consequences, or rather results or identities involving these in analogy to what we did in the binomial case. Let's go ahead on this same page and take care of the expansion, since we just did this. This says what? If n is a non-negative integer and k sub 1, k sub 2, and so on, sum to n, then this multinomial coefficient is exactly what we said it is if each k is non-negative. So this is n factorial over k sub 1 factorial, k sub 2 factorial, and so on, if each k sub I is non-negative, and it's 0 otherwise. Okay. All right. Next, we'll go in exact analogy to our binomial coefficients. We have symmetry of these multinomial coefficients. So you can use your own reasoning here to justify why this is, write a nice like one-line proof of why this has to be. Let's suppose that pi is a permutation of the set 1 through m, so we have image elements pi 1, pi 2 out to pi m. So suppose this is a permutation of the set with m objects in it labeled 1 to m. Then the multinomial coefficient is actually the same even if I have permuted those things. So k sub pi 1, k sub pi m. Okay, again, think about why this symmetry exists. This was an easier statement to make for the binomial coefficient because there's less going on, but think about why this has to be true for the multinomial coefficient as well. Think about what shuffling the labeling of the boxes does, right, to what's going on. Okay. Okay, well, what about our addition rule? So what about, we had an addition rule for binomial coefficients. What about for multinomial coefficients? So if n is a positive integer and the k's sum to n, then the multinomial coefficient n choose k1 to km. This is n minus 1 choose k1 minus 1, the rest are the same, plus n minus 1 k sub 1 k sub 2 minus 1, and all the rest are the same, and so on out to n minus 1 choose k1 k2 and so on all the way out to k sub m minus 1. This is the addition rule that we get. Again, think about why it has to be this way. If you like, try to compare the addition rule for the binomial coefficients to this for trinomial coefficients. You can actually think directly why this is. So, like, what's a proof? We'll say this is a sketch. You can kind of fill in the details here, although there's not much more to fill in other than this. So let alpha be one of the objects from the set of n total objects. It's got to be put somewhere. It's got to be put in one of the boxes, right? Alpha is in some box. If we place it in box 1, then how many ways are there to arrange the remaining n minus 1 objects to create a valid arrangement? And there are, well, n minus 1 choose k sub 1 minus 1, k sub 2, and then the rest are the same, out to k sub n. This is the number of ways there are to arrange the remaining n minus 1 objects, because I've only taken alpha out of this, to create a valid arrangement. But then if we put alpha in box 2, this number of ways is n minus 1 choose k1, k2 minus 1, k3, and then the rest are the same, to complete the assignment of objects to boxes. So then keep going, right? This is how to see that then the total number of ways of doing this is just summing each of those. Okay, summing across all of the possibilities here of alpha lying in box 1, 2, 3, and so on. Okay. All right. So previously, the second we had this addition formula, we used it to do the following. Right, so when we had the addition formula, the next thing we did, we had this addition formula for binomial coefficients. The very next thing we did was generate Pascal's triangle using it, right? So we used this addition formula to generate Pascal's triangle. So the question is there application of multinomial coefficients? And yes, this gives rise to what we could call Pascal's pyramid. Okay, so example, let's do this for trinomial coefficients. So for the trinomial coefficients, that is n choose A, B, C here, using the sum formula that we just got, we can see how to populate levels of this pyramid, to build them out, to see how this looks. Here it is. How am I supposed to think about this? Imagine this pyramid descending from the apex. This is the top. This is like the top of the pyramid. The next slice, we have a 1, 1, 1. The apex, if you like, is like above this level, right? So that we're passing one level down. We have these 3 ones. Passing a level down, we have this arrangement of these numbers. Okay, again, you can see how this 2 arises as being summed from this one and this one. Same thing with this 2, same thing with this 2. Summed from this one and this one. This 2 summed from this one and this one. Passing down to the next level, you see exactly how this goes, where these 3's come from the previous level, and so on. This is neat, of course. It's necessarily because this involves like slices of a like three-dimensional representation of this thing. Maybe view it as being a little bit less less important or less useful to you. It's harder to generate this picture, obviously, but this is very interesting, and this is more evidence that hey, this is indeed exactly the generalization that we sought. Okay, so I'm going to state the multinomial theorem. We will probably not prove it next time. I'm going to do one more example. I'm going to do one more application of multinomial stuff before moving on to the pigeonhole principle. So, but I am going to state this, and then I'll end lecture, the multinomial theorem. So if n is a non-negative integer, then x sub 1 plus x sub 2 plus x sub 3 and so on out to some x sub m raised to the nth power can be computed as a sum over integers k sub I such that k sub 1 plus k sub 2 plus and so on out to plus k sub m is equal to n of the multinomial coefficient n choose k1 to km x sub 1 to the k1, x sub 2 to the k2, and so on, all the way out to x sub m to the k sub n. This is the multinomial theorem. You can verify for yourself that in the case that you are only dealing with the x sub 1 and x sub 2 here, you're only dealing with a binomial, this reduces to the binomial theorem, so this truly is a generalization in every way. Okay, you can do this proof, like I said, by induction, and I do think that I'll at least say next time, I might spend like five minutes proving it. But anyway, that is the plan. We're going to continue on here. Didn't get to the pigeonhole principle today. That's fine. We'll start there tomorrow and do a few applications of pigeonhole principle before moving on to inclusion exclusion and then on to generating functions. So you can expect your first homework on the combinatorial stuff to be assigned on Thursday, and it'll be due next week. Next Monday specifically. So look for that. But for now, just focus on, if you haven't figured out your exam problems yet, then focus on that. That's still due this Thursday at 11:59 p.m. Otherwise, I will see you all tomorrow.